Let's answer chapter 22 review question. Question number 1. What is catenation? How does catenation contribute to the diversity of organic compounds? The answer is available on page 678. The covalent bonding of an element to itself to form chain or rings is called catenation. This property is available in the carbon. So that's why it says the diversity of organic compounds results from the uniqueness of the carbon's structure and bonding. And here it says carbon's electronic structure allows it to bind to itself to form chain and rings, to bind covalently to the other elements, and to bind to itself and other elements in different arrangements. So all of these three properties of the carbon makes the organic compound diverse. Question number 2, part A. What information about a compound is provided by a structural formula? Part B. How are the structural formulas used in organic chemistry? The answer is on page 678. The structural formula indicates the number and the type of atoms present in a molecule and also shows the bonding arrangement of the atoms. So it's not only shows what type of the atom and the number of each type in the molecule, but it shows also how those atoms are arranged and how they are bonded to each other. Usually two methods are used for showing the structural formula. One of them is shown here, which we call it uncondensed structural formula, which shows how the atoms are connected to each other, and we also shows all of the bonds. So we can easily see if there is any double bond, triple bond, or only single bond in the structure, and we can see how the atoms are connected to each other. The next one is condensed structural formula. The next one is condensed structural formula. In the condensed structural formula, we doesn't show the bond between the hydrogen and carbon, and we know that the hydrogen only forms the single bond, so it's very easy to understand that when we write CH3 it means three hydrogens are bonded to the carbon, and the bond between each hydrogen and the carbon is a single one. So we have two type of structural formula: condensed format and uncondensed format. Question number 3. Can molecules with the molecular formula C4H10 and C4H10O be structural isomers of one another? Why or why not? So we know that they cannot be isomers of each other, because if they want to be isomers of each other, they must have same molecular formula. But these two compounds have different molecular formula. Although the number of the carbon and hydrogen is same for both of them, but the second compound has one extra oxygen. So their molecular formulas are not same. That's why they cannot be isomers of each other. Question number 4. Can molecules with only single bonds and no rings have geometric isomers? Why or why not? For answering this question, first let's say why when we have the double bond we have geometric isomers. Example of the geometric isomers is like what I am drawing on the screen. So this is the cis format, C double bond. If the same groups are in the opposite side of the molecules, we will have trans format. When we have the double bond in the molecule locks at this position, which we have the double bond. So we have either of these two structures, and we cannot have both of them in the single molecule. So in a molecule, you have either this one, which the same group are at the same side, or cis isomers, or we have the molecule which is drawn on the right side. The same group are in the opposite side from each other. So the molecule is either the molecule which is written at the left, or the molecule is the molecule which is drawn at the right side. So they cannot convert to each other, and that happens because the molecule cannot rotate around the double bond. So it's double bonds are like the lock. It doesn't let to these groups rotate and hydrogen comes down, CH3 goes up. So the molecule cannot rotate around the double bond. But if we had the single bond, like the molecule which I want to draw here, this molecule, you have the carbon-carbon single bond, and in the current position, you can see that these two hydrogens are in the opposite side of the molecules. But when we have the single bond, the molecule can easily rotate around the single bond. So after the while, the molecule would be like this. So you can see when it rotates, the two hydrogen now are at the same side of the molecule. So this is a single molecule. We don't have two molecules because the carbon can rotate easily around the single bond. We have all of these positions in one molecule. So we cannot have cis and trans isomers when we have the single bond. But when we have the double bond, because the molecule cannot rotate around the single bond, we either have cis or trans molecule. Question number 5. What are hydrocarbons and what is their importance? So as we said earlier, the hydrocarbons are the molecules, or better to say organic molecules, which composed of only two elements. They are composed of the carbon and hydrogen. And why they are important? They are important because the hydrocarbons are the simplest organic molecules, and all of the other organic molecules can be considered as a derivatives of the hydrocarbons. So the hydrocarbons are the base for all of the organic molecules that we have. Question number 6, part A. What do the terms saturated and unsaturated mean when applied to the hydrocarbons? So the saturated hydrocarbons are those organic molecules or hydrocarbons which we have only single bond between the carbons. But when we say unsaturated hydrocarbons, it means in the structure we had at least one double bond or one triple bond between the two carbons. The part B of this question is cancelled. So let's go to part C. It says classify alkenes, alkanes, alkynes, and aromatic hydrocarbons as either saturated or unsaturated. The alkenes are the hydrocarbons which we have carbon double bond carbon. So this one is unsaturated. Alkanes are hydrocarbons which we have only single bond between the carbons. So the alkanes are saturated hydrocarbons. Alkynes are hydrocarbons which we have triple bond between the carbon and carbon. So they are also unsaturated hydrocarbons. And aromatic hydrocarbons are hydrocarbons which we have the benzene ring inside that, and you know that inside the benzene ring we have three double bonds. So the aromatic hydrocarbons are also unsaturated. Question number 7. Classify each of the following as an alkane, alkene, alkyne, or aromatic hydrocarbon. So this is pretty easy question. Part A, you can see that we have a benzene ring here. So this one is aromatic hydrocarbon. So this one is aromatic hydrocarbon. Part B, you can see that we have the double bond here. So this one is alkene. Part C, you can see that we have triple bond here. So this one is alkyne. And for the last one, part D, we don't have any double bond or triple bond, and we don't have the benzene ring inside this structure. So the last one is alkane. Although it is not ask us to write down the name of these hydrocarbons, but here I want to name them for more practice. In the first one, you can see we have two groups or two brands on the benzene ring. So one of them is on position number 1. We have to number the carbons inside the ring. We have to go downward because the other branch receives number 3. But if we go counterclockwise, the branch receives number here 2, 3, 4, 5. So that would be wrong. So the name of this one is 1,3-diethyl benzene. The next one is alkane, but it is straight chain alkene. We have to only mention the position of the double bond. 1, 2, 3. This one is propane. For propane, it's not important where is the double bond. Always it is in the first position. So we can just write it is propene without mentioning the location of the double bond. For the next one, we have to find the longest chain which contains the functional group or triple bond. This is the longest chain which contains the triple bond. Then we have to number this parent from the side that triple bond receives a smaller number. Obviously, I have to number it from the left side. 1, 2, 3, 4, 5. And I have one methyl branch at the third position. So this one is 3-methyl, and I have 5 carbon with the triple bond on the first position. So it's 3-methyl 1-pentyne. YNE because I have triple bond, and I put 1 here because this triple bond is in the first position. For the next molecule, the parent hydrocarbon is this one. It's the longest chain. We have to number it from the side which the branch receives a smaller number. This is the case for the alkane. So this is carbon number 1, 2, 3, 4, 5, 6, 7. On the second position I have a methyl group. So the name of this alkane is 2-methyl. An alkane with 7 carbon is heptane. 2-methyl heptane. Question number 8. Give the general formula for the members of the following alkane series. General formula is CN H2N plus 2. Alkene series, its general formula is CN H2N. Alkyne series, its general formula is CN H2N minus 2. Question number 9. What is a homologous series? The answer is on page 682. If you look at here, it says compounds that differ in this fashion belong to a homologous series. Which fashion it means? It means the difference between its member is one carbon atom and two hydrogen atom, or the difference between the members is CH2. For example, ethane and propane are in the same homologous series because the only difference between them is one CH2 group. The members of the same homologous series will have the same general molecular formula. Part B. By what method are straight chain hydrocarbons named? The name of a straight chain or unbranched chain of the hydrocarbons has two parts, the prefix and the suffix. The prefix are shown in this table. The first four prefixes are generic, meth, eth, prop, and but, but the rest of them depends on the number of the carbon. We use the Greek number. So for 5 we use pent, for 6 we use hex, for 7 we use hept, and so on. And the suffix depends of the type of the organic molecule. If it's alkane, it ends with ane. If it's alkene, it ends with ene. If it's alkyne, it ends with yne. Part C. Name the straight chain alkane with the molecular formula C10H22. Okay, 10 becomes deca or dec, and the suffix would be ane. So C10H22 straight chain alkane is decane. Question number 10. What are cycloalkanes? Definition of cycloalkane is given on page 684. Cycloalkanes are alkanes in which the carbon atoms are arranged in a ring or cyclic structure. So we can understand two things from the name. First, the cyclo, then the alkane ane. So the cyclo suggests that we have the cyclic or ring structure, and ane suggests that we have only carbon single bond carbon. What is important here, you should not confuse cycloalkane with the benzene ring, especially cyclohexane. The structure of the cyclohexane is like this. We have only single bond between the carbon and carbon, and each carbon is bonded to two hydrogens. This is cyclohexane. But the benzene ring, it is also 6 member, but we have 3 double bonds inside it, or we have delocalized electron inside it, and 1 hydrogen is bonded to each carbon. So don't confuse this aromatic hydrocarbon, which is benzene, with the cyclohexane. You can understand the difference between them from this circle which is drawn inside the hexagon structure in benzene. Question number 11. What trend occurs in the boiling point of alkanes? So for the alkanes, by increasing the number of the carbon, the boiling point also increases. Part B says, how would you explain this trend? Okay, the hydrocarbons or alkanes are non-polar molecules. The only force of the attraction between their molecules are London dispersion force. And the London dispersion force depends on the number of the electron inside the structure or how massive is the molecule, because by increasing the number of the carbon, the molecule becomes more massive, the chance of formation temporary dipole increases. It means the London dispersion force becomes stronger. That's why the boiling point of the alkane increases. Part C. How is the trend in alkane boiling points used in the petroleum fractional distillation? In previous video, we have talked about the fractional distillation. We have a column or fractional column which has the different temperature, and we separate these hydrocarbons based on their difference in boiling point. So we can use fractional distillation for separating the alkanes based on the difference in their boiling point. Question number 12. Give examples of ethane's commercial uses. So one of the famous example of ethane is we use it as a hormone for the fruit ripening. The commercial use of the ethane is written here in the textbook. It says it is used in the synthesis of the many plastics and commercially important alcohols. So we use them as a precursor for the making plastics and alcohols. Also, we use them as a hormone for ripening of fruits. These are two commercial use of ethanes. It is written on page 693. Question number 13. Give one use of ethane. Ethane is used in the welding torches. Question number 14. What is the name of the parent hydrocarbon of simple aromatic hydrocarbon? The simplest aromatic hydrocarbon is a benzene. Question number 15, 16, 17, 18, and 19, and also 20 we have answered in previous videos. You can go and watch them. So we have answered all of the questions which are related to the section 1 and section 2 of chapter 20, and this would be the end of your class.